the sinusoidal nature of simple harmonic motion, the period of a pendulum, and wave motion. Okay, so I want to talk with you about finding position as a function of time as something is moving through simple harmonic motion. And first I want to talk with you again about what this looks like on a graph as time passes. So imagine I have a mass attached to a spring, and let's say the spring is stretched all the way to the right at its maximum amplitude, and that's where time is going to start. So time is going to start up here at the amplitude. And then as time goes on, we get a graph that looks something like this. So one whole cycle, or the time for one whole cycle, would be the period, and that would be from crest to crest. So this would represent one period. Half of a period would be at this point right here, 1/2 t. And as you can see, since this object started where it was either stretched at its maximum position or possibly even compressed from its equilibrium position, we can say that we have a cosine function here. And so since we have a cosine function, our position as a function of time will have cosine in it. And the formula we're going to use for that is x as our position is equal to the maximum stretch or compression, otherwise known as our amplitude, times the cosine of 2 pi multiplied by the time that we're interested in the problem, divided by the period. As you know, because period and frequency are inverses of each other, we could also say then our position is equal to the amplitude multiplied by cosine of 2 pi, the frequency multiplied by the time. At this point, I also wanted to review with you how to determine your maximum velocity and your maximum acceleration when your object is at different positions when it is in simple harmonic motion. There are a couple formulas for this. So your V max is equal to 2 pi multiplied by your amplitude multiplied by your frequency, and that is equal to your amplitude multiplied by your square root of k over m. So these are some formulas I would like you to memorize. And there's also a formula for finding maximum acceleration, and we should know this as well. And of course we know acceleration is equal to, or force is equal to mass times acceleration, or acceleration is equal to force divided by mass. We know because of Hooke's law, that's negative kx over m. And actually we have our maximum acceleration if our x value is equal to our amplitude, where we have a maximum stretch or compression. So that's actually negative ka over m. So that will give us our maximum acceleration. Now going back to position as a function of time, I wanted to look again at a graph if we have a different situation. Now the first situation in letter A was if the object had a maximum stretch or compression and we had a cosine graph. But what if the object starts from equilibrium position, although it has an initial push or an initial speed? Then we would have a function that looks something like this. And we call that a sine function. Note that I drew in on the vertical axis that the maximum distance will give us our amplitude above and below equilibrium position. But now we have a sine function, so we can have another formula depending on the condition of your simple harmonic motion. If the object starts at equilibrium position with, say, an initial push to the right, if we're talking about horizontal motion, then we will have a formula for position as a function of time that looks like this, that x is equal to the amplitude sine times the quantity 2 pi ft. Alrighty, let's go. Let's do an example. Okay, so in this problem we have some sort of simple harmonic motion where there's a frequency of 262 hertz. There is an amplitude of 1.5 times 10 to the negative 4 meters, and at time equals 0, the position away from equilibrium position is maximum, or it's the amplitude. And what this means is that we therefore have a cosine function, cosine condition. So your goal is to find an equation to find motion as a function of time. The formula for simple harmonic motion to find position as a function of time, the general formula is your position is equal to A cosine 2 pi frequency multiplied by the time. So plugging in here, for my amplitude, I will have the 1.5 times 10 to the minus 4 meters cosine of 2 pi multiplied by the frequency of 262 hertz multiplied by the time. And so ultimately that gives me 1.5 times 10 to the minus 4 multiplied by cosine of 1,650 t. So if you knew the time involved in this problem, you can plug that into your equation and then you can find your position. Please make sure that your calculator is in radians and not degrees when you are using the formula with the cosine function or the sine function. Okay, now I want to talk with you about the simple pendulum, and basically what is the period and the frequency for a simple pendulum. So for angles from equilibrium position less than 15 degrees, this applies. And so what we know is the period of a pendulum is equal to 2 pi times the square root of L, which is the length of the pendulum arm, divided by G, which is known as the acceleration due to gravity. And since period and frequency are inverses of each other, then the frequency will be 1 over 2 pi multiplied by the square root of G over L. So really the only two things that we're interested in when we are determining period and frequency of a pendulum is what planet are you on, because the planet you're on will tell you what your acceleration due to gravity is here, and what is the length of your pendulum arm. What is the length there? And if you know those values, you can figure out your period or frequency. And the mass of your bob is unimportant. But of course this does depend on whether the size of your angle. So your angle away from equilibrium position must be less than 15 degrees. Okay, so now I want to talk about wave motion, and I want to specifically talk about wave motion with mechanical waves. And mechanical waves are just waves that are moving through a medium, like waves that move through water, or a wave that may move through a string, or even sound waves that may move through air. These are mechanical waves. Now when we're talking about mechanical waves, you may hear the term pulse. And a pulse is just a wave bump. Let me give you an example. This would be like a little bump along a string, maybe moving to the right, for example. And this little bump would have a name of, because it's at the top, we would call it a crest pulse. Okay, so let's talk about the anatomy of the wave. We've probably already talked about most of this already, but let's talk about it just a little bit more. So this would be an example of some sort of sine wave, perhaps. And we know that we have an amplitude here, which is from the midpoint to the very top, or from the midpoint to the bottom. This is our amplitude. Our wavelength here is basically when the wave starts and then when it starts to repeat itself. So that would be equal to one wavelength. But you can also say it's from crest to crest or from trough to trough. And that's equivalent to a wavelength. Of course, this very, very top part of this wave right here is known as a crest. And the very bottom portion right here is known as a trough. There are two formulas that you should know when we're dealing with wave motion, and you should memorize this. One is the speed of a wave is equal to the frequency of the wave multiplied by its wavelength. And there is another formula for the speed of a wave on a string, and that is equal to the square root of the quantity of the force of tension of the string divided by the mass per unit length of that string. So notice that more tension is in the string, the faster the wave is going to travel down that string. And that should make sense if you're dealing with a violin, for example, which is a stringed instrument, and you can tune that instrument by tightening or loosening the string, which could therefore affect the speed of the wave and possibly even the frequency of that wave and therefore the pitch. Okay, so 3 problems for your practice on pages 317 to 318, numbers 19, 33, and 41. Good luck.